In the first part of the second lab, we're talking about projection, coordinate reference systems. And you might think, well, this is wirehead abstraction that doesn't really impact me or doesn't really matter much to me. And the purpose of this video is to sort of introduce the stakes of this and explain why you should care. The bottom line is the reason you should care about projections is it is a basic property of the files that you're opening. And if you have files that are referenced differently, it can, at the least opportune time, create catastrophic problems for you in GIS. It probably won't for you this semester, not much, but it can be a source of woes, and that's why we put it right up front. Here's what projection is, and here's how it works. Now, to think it through, I think it's a lot easier rather than talking about it from slides in the abstract, even though I think that stuff is interesting. I think the best place to start is by seeing the consequences of projection. So here I have a blank screen. I said open, start without a template and just have nothing going on in this map. And I'm just going to say insert new map. So Arc is opening a map for me. By default, when it does that, we can check the projection properties of the map it's opened, and we'll see that the spatial reference that it's using is WGS 1984 Web Mercator. So even though we don't even have any data here, think of this as being a frame. I think of it as a Jello mold into which we're dumping our data, and it's going to influence how our data appear. Now we can change that to something else. What I want you to notice, though, is this is the default setting. You can change it if you wanted its default to be something else, like UTM Zone 18N based on the North American datum of 1983. You can say that's my default setting. Anytime I open a map, it's going to look like that. Until you do, when you have a brand new screen, it's in what's called WGS 1984 Web Mercator. Now that might not mean anything to you, but the thing to know about WGS 1984 is that is a model of the shape and size of the Earth. It's called an ellipsoid model. It's a mathematical model based on the actual properties of the Earth, but the Earth's kind of lumpy. We'll learn more about that later. And this is the mathematical model of the Earth that the Global Positioning System uses. So when you have coordinates coming off a GPS, unless you tell it to do otherwise, those coordinates come at you using degrees of latitude and longitude based on the ellipsoid model WGS 1984. Now this, in this particular case, the default projection, and it's easier to see this if we insert a base map. So if we throw some imagery in there like terrain with labels, we can see better what this coordinate system does. So here is WGS 84 Web Mercator. Now you'll notice Antarctica is really elongated. The farther you get away from the equator, the more things get exaggerated north and south, which is problematic. But Web Mercator does a particularly good job of maintaining direction. This is something we're going to talk about later. Now I want to compare that to what happens if I add a new map. And in this case, I'm going to put in the point location of the random point I made in Lab 1 when I was running through this myself to make sure I could do it with my GPS. And when I was sitting in Sondheim Hall, I created a waypoint. So there is my point location. This is Sondheim Hall. And if I look at the attribute table for that, I don't have a lot of information about it, but I do have the latitude and longitude. So those are degree measurements. How far west of the prime meridian are we? It's 76 degrees, about -77. And then how far north of the equator are we? About 39 degrees. If we look now at the Map 1 data frame, so this is comparing our first map called Map to Map 1, which is the new map I inserted to draw this single point. Now we're in WGS 84. It's no longer Web Mercator. Why is that? Because the first file you open in an ARC project establishes the spatial reference for that map. Sometimes this is called a data frame. So for the Map 1 data frame, the coordinate reference system that we're using, the spatial reference that we're using, is WGS 1984. The same one, by the way, used by the Global Positioning System. So why are we using this reference? because that point that we imported from the GPS came from a GPS, and the GPS says, by the way, this is in WGS84, these numbers I'm handing you. If it had handed us numbers in a different coordinate system, which it could have, we can tell it, use a different coordinate system, so a different basic model of the shape and size of the Earth, we would have something like NAD83 instead of WGS84. WGS84 is how those points came to us. And now if we do the same thing we did before and insert that base map, we'll see that the world looks different in WGS84. So let's compare that to the original map, in which we have things really elongated north and south. You can compare those and say, oh, okay, so we're depicting the world in a different way. Finally, I'm inserting here, or I have inserted, a third map named Map 2. Go figure. Just like the other maps, when I first inserted it, it would have been in WGS84 1984. And just like in the previous iterations, by insert, or just like in Map 1, by inserting a new shapefile, I've changed the spatial properties. So remember, when you have a blank screen, the first file you open determines what the spatial reference is for everything else to follow, unless you tell it differently. So I've inserted this time the campus waypoints, the objects that we gave you at the beginning of the first lab. And these waypoints, it turns out, are in USA contiguous Lambert conformal conic, and if I did it right by copying and modifying, they are centered on not the 96 meridian, but the 76 meridian. Why do we do this? Because the longitude of Baltimore is somewhere between 76 and 77 degrees, and so by centering it there, our map is centered on our location. We'll talk more about what that means, or what the implications of it are, but if you want to check out the difference, insert a map in which you don't make this change, insert a map in which you do make this change, and you'll see they look really different when you zoom out to the scale of the world. Often these differences are barely detectable when we first insert a map, because when we're zoomed way out, it's harder to see the difference, when we're zoomed way in, when we're looking closely at something, the differences are very small. The reason we change projections is because some are better suited for different scales. And I'll talk more about that when we talk about projections in more detail. But for now, suffice it to say, this is in Lambert conformal conic, and you'll notice a couple things about that. First off, down here at the bottom, notice these numbers. Those are telling us our coordinates. So wherever I put my pointer, like at this location, it's telling me what the latitude and longitude are. What numbers is it using? It's using these numbers that are in the thousands, 61,325.73. That tells you that we're not working with degrees. We're working with some other way of marking latitude and longitude. And I'm showing you this because the difference between Map 1 and the original map is that both of those maps are showing us things in degrees. So if you go to our location or somewhere near it, you'll see we're like 80 degrees west of the prime meridian and 37 degrees north of the equator, so we're not quite on campus. Getting close. The other map does the same thing. It's telling us where we are, our location, in degrees. This last map is telling us our location relative to some imaginary origin, which is down to the lower left-hand side of the map, off the map entirely. You see in the map, I can't get any smaller than like 61,000, almost 62,000 feet, or probably meters, east of some false origin and north of some false origin. We're going to talk about what that means, but the idea here is there are two different types of coordinate reference systems, basically. And you can take a look at the PowerPoint slides for the presentation I'm giving this week. You'll see that some of these coordinate reference systems refer to locations on a globe, and some of them refer to them as though on a sheet of paper. And so they just reckon things differently. The real fundamental difference for us is if you want to measure distances, like how far apart are these 2 points, like the tool we did in lab, this is telling you that these 2 points are about 115 meters apart. it's much more difficult to measure those distances because it's measured in degrees, not in miles. And so if you want to reckon things in a linear unit, it's better to work with what we call a projected coordinate system than a geographic coordinate system. That's a fine distinction that we make, but it's an important one ultimately. Now when we zoom out in this coordinate reference system here, you might remember we've done this before to compare map 1 and map 0 and just seeing how different they look depending on the coordinate system we use. Map 2, which is based on the Lambert conformal conic, looks different still. Now those differences you don't notice much zoomed way in, but when you zoom out, you'll notice that the overall rendition of the Earth gets more and more contorted the farther you get away from our point location. So this is a really helpful coordinate reference system to use if you're working at a regional scale. But if you get far from Baltimore, it gets less and less useful. You can see things get kind of tilted and weird looking the farther away you get. And that's just sort of the pitfall of choosing one coordinate system over another. One other thing to bear in mind with coordinate reference systems is when you're using these, that what you really want to do is at the beginning of any project, sort of like I've said before, take a look at things, inspect what you've got. You'll notice I've got catalog pane open on the right. Check the properties of each file before you bring it into the map so that you know, oh, this one's in WGS84, or this one's in Lambert conformal conic, or maybe they're all in the same thing, but maybe they're not. By checking them, you can think ahead about a couple things. Often it's a good idea to project the files so they're all the same before you start, and that's a way of preventing really big catastrophes from occurring in the middle of a big project, and you're going, oh my God, what's wrong with this? And you think, oh, it's a projection problem. I kind of need to start all over. That's the crisis I want you to avert. By checking the properties of files before you begin, by checking the data frame properties, by clicking on the map and looking at the spatial reference of the map, as well as the spatial references of your data, you can say, well, let's just make them all the same now before we begin, and then we won't have those catastrophic problems later. That's why we're talking about this at the very beginning of the semester, by the way.